Hi everybody. In this tutorial we're going to introduce horizontal projectile motion, and the goal for this initial tutorial is really just to take us through the concepts and get through basically this graph for the situation and down here. The problems that follow we'll do in class to reinforce. So what we want to understand is how our kinematic equations and VTAX applies to projectile motion. So we're going to build it around an idea where we have a cannon right here that's on some cliff that's a height of 80 meters, and we're just going to fire it horizontally. Eventually, we're going to learn how to deal with it when we fire it at an angle, but the general concepts we're learning here apply for at an angle. It's just the math is just a little bit more complicated. Okay, so let's get to it. What we're eventually going to want to do is plot where the cannonball is at certain time intervals. And we're going to use our kinematic equations. I'm going to show you where they come from, and hopefully they make sense. There's a lot of little nuances here and other things that if I have time in the 15 minutes I get to, otherwise we'll address them in class. So before we can start applying the kinematic equations, well, I've already put them right here and here, you got to ask yourself, where did those come from? And that's understanding at the heart of all projectile motion, when this ball is fired and it's fired this way with some velocity, it's going to do two things at once. It's going to go forward, and at the same time it's going to fall. And so we have horizontal motion and we have vertical motion happening simultaneously. What we want to do to help us understand predicting where it's going to land, how much time, speed, etc., is we must keep those two directions, horizontal and vertical, independent of one another. We treat them separately and then we combine them to get one full motion. So to understand how to do that, we got to look at what's true of each. Horizontal motion and vertical motion. So fill in these blanks. This is the heart of everything projectile. If anything, this is the new stuff. Everything else, as we've already learned, we're going to apply to that. So horizontal motion, as soon as this ball or anything leaves the thing that's firing it, throwing it, releasing it, whatever, it is constant motion. Okay, it moves at a constant speed because we are ignoring any effects of air resistance. If there was significant drag, this would not be true and the math would become calc-based level, which we're going to avoid. Vertically, well, we're under the influence of gravity as soon as it leaves the barrel, and so we've learned already that that's accelerated motion. And in fact, it's not just any acceleration, it's going to accelerate at a rate of g in the vertical direction, not the horizontal. Horizontal is constant. Okay, so if I want to plot where is this marble after a certain amount of time, in fact, I've chosen time 0, 1, 2, 3, 4 seconds, we got to apply two different equations, one for the horizontal and the fact that it's constant speed, and one for the vertical. Now, what I want you to understand before I'm going to show you where these equations came from. You can probably anticipate it, but it's worth checking. So I'm just going to go to a blank page here. So horizontal is given a direction x. And if I want to know where anything is at a certain time, I can use the generic equation x naught plus v naught. And now I'm going to put an x there to indicate the horizontal times time plus 1/2 ax, again, horizontal acceleration, times t squared. If I want to do the same thing, but for the distance it falls, the vertical, I call that y, well, that's going to follow the same pattern here. It's going to be equal to our initial height, y naught, plus v naught y. So notice the difference between here and here. This is the vertical initial speed. This is the horizontal. T is still t. Now, here's where things I'm going to do off the side. Normally we put 1/2 ayt squared. But what do we know about the vertical acceleration? Well, that's just g. And since g is down, I'm going to put in the minus here, so it becomes minus 1/2 gt squared. Okay, so these two are essentially the same equation. It's just that we're applying them for two different directions. So now we can use the fact that we learned on the front side where we said horizontal speed is constant. If horizontal speed is constant, that means this is 0. And if our initial position is 0, which is the assumption here, we can see where we get x equals vt in the x direction. So if I go back to here, that's where I get x equals vxt. I just didn't put the v naught x in there, but that's implied because the speed is constant. It's the speed at any time. If I go to the vertical, well, it's accelerating, so this part is definitely still there. But what's true of the initial vertical y? The vertical initial speed is 0 because it wasn't launched up or down in a general direction. It was launched forward, which means no vertical. Did it start at 0 height? No, in this case, it started at some height. In fact, it's 80. So if I look at the equation of where are we vertically, that becomes y minus 1/2, or y naught minus 1/2 gt squared. So that's where this equation comes from. Okay, now we can start applying the two equations. So I'm going to start with the x. Where is this cannonball after 0 seconds? Well, at time 0, that's the moment it leaves the barrel. It's at position 0. And then after 1 second, if I do 10, right, it's fired at a speed of 10 meters per second. 10 times 1 is, of course, 10. Then I can do 10 times 2, which is 20. 10 times 3, 30, and 40. Okay, so it's going to move forward the same distance each time. And so don't put this down yet. If there was no gravity, if this was fired in a gravity-free zone, right, here's where the cannonball is at time 0. After 1 second, which is what this hash mark is, so I'll go down here, there's 1 second. It's going to be here. It's going to go 10 meters. We're going to assume this interval is 10. And then after 2 seconds, it's going to go the same distance. 10, it's going to go the same distance, same distance. So that's the hallmark of constant speed. It covers the same distance each time interval. But of course, gravity is not 0, it's something else, so we know it's going to fall at the same time. So now we want to add into this the vertical part. Okay, so I trust you can do this correctly, but I'll do a few together. So what is our height at time 0? Well, it's our initial height, which is 80, minus 1/2 gt squared. Since time is 0, that's just going to be 80. Whoops. Okay, so in other words, at time 0, our initial height is literally 70, 80 above the ground. Now let's see how far it's fallen after 1. Actually, not how far it's fallen, but what height is it, which is where we started, minus how far it's fallen. Well, this is going to be y naught, 80, minus 1/2, and we're going to say g is 10 here, 10 meters per second per second. I know there's a lot of 10s in this problem, but hopefully that's not confusing. Rather than using 9.8, 10 is much easier. So I can say 10 times 1 squared. 1 squared is 1 times 10 is 10. Half of that is 5. 80 minus 5 is 75. If I do it after 2 seconds, I'm going to do 80 minus 1/2 of 10 times 2 squared. 2 squared is 4. 4 times 10 is 40. Half of 40 is 20. 80 minus 20 is 60. Okay, now if I do the same thing, and I'll leave it to you to verify it, after 3 seconds, I'm going to do it right now. 3 squared is 9, 9 times 10 is 90, half of that's 45, 80 minus 45 is 35, and then after 4, 4 squared is 16 times 10 is 160, half of that is 80, 80 minus 80 is 0. In other words, we hit the ground after 4 seconds. So watch this. Now we're going to plot those coordinates. So at time 0, we were at height 80. We've already got that point. I'm going to go to, I'll just leave it blue since, actually, can I move this bar? You can't see that. All right, I'm going to go to red now. So there's where we are at time 0. At time 1, so I'm going to go over time 1, we are at height 75. So here is 75. At time 2, we are at height 60. So 2, and then I'm going to intersect right there at 60. There's time 2. Time 3, I'm at 35. And hopefully I haven't misaligned anything. So there's at time 3. And then time 4, I'm at the ground. I've fallen the whole thing. And if I look at those 5 dots, they trace out the path. And whoops, that was pretty bad. If I follow that, I don't get a straight line. I get a curve, and it's not just any curve. It's a very specific curve. It's a parabola. It's a parabolic arc. Now, the AP expects you to know why it's a parabola. Okay, there's 2 ways you can look at it. One way to look at it is the x, the horizontal, changes with time, whereas the vertical changes with the square of the time. When you combine both of those, you get a parabola. That's, in a sense, the ax squared plus bx plus c kind of approach. I want you to understand this from a conceptual approach. And the explanation that you expected to know and you will be tested on is a parabola, because in one direction, that's the horizontal, is constant. We already said that. And in the other is accelerated. Sorry, this is so sloppy. I'm just going to put Excel. In other words, in any situation, not just projectile motion, if you have two directions of motion that are perpendicular, in this case vertical and horizontal, and one is a constant speed and the other is accelerated, you must get a parabola. Now you might say, well, what are the other possibilities? Well, so don't draw this in, but you can imagine something could fall in a straight line, right? Why doesn't it fall and move forward at the same time? That would be true if both motions were constant speed, which is not the case here. Or if both were accelerated. So if both were constant, I don't know if you want to write that because we're going to need this space for something else, both constant or both accelerated, then you get a straight line. Okay, so you need to understand those three when we're comparing two independent perpendicular directions. Alrighty, so I'm almost done with this. I just want to talk about a few more possibilities conceptually before we worry about solving a specific problem. What if I had fired this with an initial speed of 5 meters per second? Sorry, that's supposed to be a 5. Okay, we're not going to do all the calculations again, but we could ask what would be the same, what would be different in comparison to this flight. Well, I think you know intuitively if we fire it slower, it's not going to go as far. It's going to land somewhere, let's say here. In fact, we'll eventually show that if the distance was way out, oh, this is time here, it would, that's interesting. Yeah, it would not go as far each interval. It would go half as far, and so it would be something like this, okay? And if we fired it faster, let's say at 50 meters per second, it would be a parabola that's much more stretched out, okay? What I want you to understand is it has to fall immediately. What would be the same in all three cases is the time in the air, the acceleration, and the vertical speed. What the point being is, what did I change? I changed this, which is a horizontal thing, the horizontal and the VTAX. It does not affect anything vertical. Okay, so I'm just about done. One last thing. So when we go to do problems where something is launched horizontally, eventually we'll learn how to do it at an angle. When determining the unknown and given information, you need to make two columns. Our VTAX is right here. I've just put V final at the end because it's usually not important here. So these are the four main players: initial speed, time, acceleration, that, and I need to do it two columns. X is horizontal. Well, I'm not going to write that all out. Okay, that's an H for horizontal and V is for vertical. They're independent. I cannot combine them. I got to treat them separately. So we'll do a problem based around our marble launcher. Okay, if you want, right now, you can look at this information and fill out VTAX and stop there. All right, if you have questions, make sure to ask.